Well, dear students, in the last video I told about the uniformity of the gas molecules in case of kinetic theory of gases. If we are discussing about its kinetic properties, then we need to understand uniformity. Means at any point you go, at any point you will find defined velocity of the particle and all possible velocities everywhere throughout the volume. That was the best assumption, the most important assumption which was taken, and after that we can come to make further calculation. And in my point of view, from my point of view, this particular derivation is marvelous in itself, and if you understand it completely, then there are lots of situations where you may get stuck up, but if you have gone through this, then definitely you will crack every problem of thermodynamics related to KTG, kinetic theory of gases. Even this can further relate to the specific heats. It can further relate to the thermodynamic processes, the fundamental thing, because the whole thermodynamics is based on the basic assumptions, hypothesis taken for the kinetic theory of gases, and this particular derivation makes that assumption stronger, that the calculations are also carried in the same way. You may have book in your hands. I am reading it just word to word. The heading is calculation of the pressure of an ideal gas. I'm reading it, and wherever the explanation will required, I will give it. Consider an ideal gas enclosed in a cubical vessel of edge L, taking a corner of the vessel as the origin O and the XYZ axis along the edges, as shown in the diagram, right? Let A1 and A2 be the parallel faces perpendicular. These two faces, look here carefully. This is A1, this is A2. These are two parallel faces. Parallel faces perpendicular to the x-axis. Consider a molecule moving with velocity v. The component of velocity along the axis are vx, vy, vz. Definitely, if the molecule has velocity v, then we can take its components. Those are vx, vy, and vz. When the molecule collides with the face A1, the x component of the velocity is reversed, whereas the y and z component remain unchanged. I hope in class 11th, when you studied in 2D collision, let me explain here. Let a ball comes in this way. It comes in this way. And this is x-axis. This is, say, y-axis. Now, if ball comes and strikes with this wall or floor, right? This angle is alpha, this is alpha. It strikes with velocity u. Then it has one component u cos alpha and another here u sin alpha. It rebounds, goes here with velocity v. This is beta. Then you take component v cos beta, and here v sin beta. I hope you remember, in the later phase you equate these two. V sin beta is equal to u sin alpha, but v cos beta and u cos alpha are not equated. These are equated if the collision is elastic. I hope you are getting this point. If this had x component, y component, the force exerted by the wall on the particle is always along the normal direction. So in this case, the normal direction is y only. The x and z, there is no force. So x and z components of velocity will remain unchanged. Only y component will get changed. If the collision is inelastic, then there was some relation v cos beta is equal to EU cos alpha. Let me write it. V cos beta EU cos alpha. And if the collision is elastic, then E equals to 1, then V cos beta also becomes U cos alpha, but the direction is reversed. Now the force, the normal force, doesn't change the magnitude, but direction is reversed. The same thing is explained here at this point, that when this particle collides with A1, the component of velocity along the axis are Vx, Vy, Z. When the molecules collide with the A1, the x component of velocity is reversed, whereas the y and z components remain unchanged. This follows from our assumption that collision of the molecule with the wall are perfectly elastic. Now here it is assumed that collision is supposed to be perfectly elastic, then direction is reversed, but the magnitude remains same. The change in momentum, in this case I hope you know very well, the change in momentum is mv minus mv, or I take this direction, first direction in the positive, then it is delta p is minus 2 mvx. The magnitude of change in momentum is 2 mvx. As the momentum remains conserved in a collision, as change in momentum of the wall is delta p dash 2 mvx. After rebound, this molecule travels towards A2. The x component of velocity equal to minus Vx. Now, after striking with A1, the molecules move towards A2 with the same speed Vx. Any collision of the molecule with any other phase except for A2 doesn't change the value of Vx. Now, any collision of molecule with any other phase except A2 doesn't change the value of Vx. In the same way, now this statement says what? Any collision of the molecule with any other phase. Look, the x component can be changed by A1 or A2, only these two phases, because the x component is perpendicular to these two phases. Rest all the phases are parallel to x-axis. So this statement says any collision of the molecule with any other phases. As I explained here, when it collides with A1, then y and z components are not changed. So A1 and A2 can change only x. In the same way, other phases cannot change x. Only these two phases can change x. Perpendicular faces to the y-axis, for example, these two faces can change y. Perpendicular to z, these two faces can change z. Now Vx, Vy, Vz, these three components can be changed by two faces which are perpendicular to their axis. Here need not to get confined only with the x-axis. We can discuss for y and z also. Now x component can be changed by A1 and A2, the faces which are perpendicular to x-axis. In the same way, there are two faces you can see perpendicular to y-axis. One is front, this face, and other is back side, this face. The z component can be changed by this face and this lower face. Getting? So each component can be changed by any of the two faces which is perpendicular to the axis of that component. So this statement says that any collision of molecule with any other phase doesn't change the value of Vx. What is? Only A1 and A2 can change. So it travels between A1 and A2 with a constant x component of velocity which is equal to minus Vx. Now this is a very clear statement. So it travels between A1 and A2 with a constant x component. It's not said it's constant velocity. It's said it's constant x component of velocity which is equal to minus Vx. And in the previous video I explained, you consider the uniformity. If it collides with another particle, the another particle will acquire its Vx and it will move. If again it collides with another particle, the another particle will acquire Vx. Like other people will do work for other particles, will work for this single particle, and it will look like that is the same particle is moving from one end to another end. Note that we can neglect any collision with the other molecules in view of last assumption discussed in the previous section. You can go through the previous section. So we can consider a single molecule is moving. The distance travelled parallel to the x direction between A1 and A2 is equal to L. Thus the time taken by the molecule to go from A1 to A2 is L by Vx. The molecule rebounds from A2, travels A1 and collides with it another time. Now look, A1 to A2, it travels distance L with Vx along x-axis, then returns back and travels distance L again, then total distance is 2L. Then we can say that if at t is equal to 0, it collides with A1. Then further time delta t, it takes 2L upon Vx because it has to travel L in this way and L back. Then this is time delta t 2L by Vx. Sometimes students get confused at this statement. This is given frequency. No need to go in this way. If you can understand, of course you understand in this way, that force is what? Delta P upon delta T. So here you can, I say here delta F is delta P is 2 mvx upon delta T you can take, and delta T is what? 2L upon Vx. So delta F becomes 2 mvx 2L upon Vx upon delta T. Here it is. Now it becomes delta F is equal to 2 to cancel, it becomes mvx square by L. You can take in this way also, because the term frequency and sometimes students get confused. This is n, or I say delta F here. It is mvx square by L. Further, this is also the force exerted on the wall A1 due to this molecule. The total force on the wall A1 due to all the molecules. Here we have put a sign summation. Summation says means considering all the molecules. As in many situations in mathematics we have seen, we can say that if I say delta F is equal to mvx square by L, then F is summation of delta F I equals to 1 to n. In higher mathematics, need not to write the limits. We can simply say this also. So here it is written as summation mvx square by L. In this way it is written. So it contains, this summation contains all the n molecules, right? Further we move. It is n m by L Vx square. As all the directions are equivalent, this is very important. We have now look. Every particle has equal probability of velocity in all the directions. Then at any moment, as you see that you take a balloon, you press it from anywhere, it will return back to its position, and it is the balloon is inflated uniformly. That means the molecules inside are continuously colliding with every point inside the balloon every moment. So if we consider in xyz axis, then we can say that velocity having component in all these three possible directions must have equal probabilities. Now here the important thing is that it's not said that Vx square equals to Vy square equals to Vz square. It's that summation of Vx square equals to summation of Vy square equals to summation of Vz square. Now this particular line makes you very much clear about the assumption which was carried in the on the last page, that if we are taking large number of molecules, then the collective their x component square velocity, y component square velocity, z component square velocity are same. It is not about an individual particle. It's taking collectively all the particles. It is clearly written as summation. It hasn't, no one's no equation is like this, that vx square equals to vy square equals to vz square. No, it is summation vx square equals to summation vy square equals to summation vz square. Means taking all the particles once at a time, large number. If this becomes a large number, then it average of these three, vx square, vy square, vz square, is same. If all these three are same, then how these, this is the students are confused here, how one can jump here. Okay, let me explain here. Look, it is written summation of vx square, summation is equal to summation of vy square is equal to summation of vz square, right? All these three are equal. Now if I add all these three, summation vx square plus summation vy square, I am not putting equal to sign here, okay, I am just adding it, I am putting this sign, plus summation vz square. Then as I have told that these three are equal, say this is alpha, this is beta, this is gamma, then, and it is said that alpha is equal to beta is equal to gamma, then can't we say that alpha plus beta plus gamma divided by 3 is also equal to this? Very clear. It's so general, it's so easy to say. So here we can say that summation of vx square, summation of vy square, summation of vz square equal to 1 by 3 summation of vx square plus summation of vy square plus summation of vz square. In this way it is set. Got it? So this gets clear, because here after this step student lose their say spirit ki we can't understand H. Verma. Now once again, summation of vx square plus vy square plus vz square. Now this becomes what? Total velocity. It is summation of v square. I am saying again, this is again summation of v square. Later it will be written, here I should write that 1 by 3 summation v square means 1 by 3 v1 square plus v2 square plus v3 square, so on up to vn square. This means this actually. Got it? It is not velocity of single particle. Now there is 1 by 3 summation v square. F becomes, here we come back, that was vx. Now vx, in place of vx we have written 1 by 3 v square. F equals to 1 by 3 m by l summation of v square. Here it was vx square, here it is vx square. Vx square becomes 1 by 3 summation v square. F equals to 1 by 3 m by l summation of v square. Further, if n is the total number of molecules in the sample, we can write F equals to 1 by 3. I have at this step, the equation is divided and multiplied with capital N. N numerator and denominator. This Mn will become mass. This N is total number. Now what is done here? The F calculated was 1 by 3 m by l summation v square. Now what is done here? Divide and multiply by n. 1 by 3 mn summation v square by n. Now this Mn becomes the total mass, and this summation V square by N, this is average of squares, V1 square, V2 square, V3 square, N squares divided by N. This is average of the squares, 1 by 3 Mn by L. Further, pressure is defined as force upon area. Area, it is square, we multiplied by L square. Mn, it becomes L cubed, summation V square by N. Now we turn here, L cube. L cube is what now? In place of small mn, total mass is written here. M by L cube, it is 1 by 3 rho, summation V square by N, where M is the total mass of the gas taken and rho is its density. Also, summation V square by N is the average of the speed squared. And I told you before, it is written as V bar square. We can write here known, and it's called mean square speed. Thus, the pressure is P equals to 1 by 3 rho V bar square. This term is written as V bar square. Rho is M upon V, then V comes here, then PV 1 by 3 M V bar square, and further we can write again in place of M N into M particles. Got it? This is about this theory. Definitely you need to go through the book once, and once you get this section in your mind, then the whole KTG becomes very easy for you.